In section 4.7, we are looking at the change of basis. So here we're going to explore how the coordinate vectors of two distinct bases are related for all vectors x in some vector space V. So here we go. Here is our change of basis formula. So to begin, we are going to let B be a basis defined by the vectors b sub 1 through b sub n, and we're going to let C be a basis defined by the vectors c sub 1 through c sub n, and these are two distinct bases in some vector space V. So then, there exists a unique n by n matrix, P from basis B to basis C, such that the coordinates of vector x relative to basis C are defined by the multiplication of the change of coordinates matrix from basis B to basis C and the coordinates vector of x relative to basis B. So how do we write this? Well, we have the coordinate vector of x relative to basis C is defined as the product of the change of coordinates matrix from basis B to basis C and the coordinate vector of x relative to basis B. So then, the columns of the change of coordinates matrix from basis B to basis C are the C coordinate vectors of the vectors in basis B. So this means that we define our change of coordinates matrix P from basis B to basis C as the matrix whose column vectors are the coordinate vectors of the basis B relative to basis C. So we have the coordinate vector b sub 1 relative to basis C, we have the coordinate vector b sub 2 relative to basis C, and we continue all the way to the coordinate vector b sub n relative to basis C. And this is what we call the change of coordinates matrix. And this is specifically the change of coordinates matrix from basis B to basis C. And so what is this change of coordinates matrix doing? Well, it's taking a vector in basis B and mapping it to a vector in basis C. So the multiplication by the change of coordinates matrix from basis B to basis C converts the B coordinates into C coordinates. And that's what we're seeing up here. We're seeing that the multiplication of the change of coordinates matrix with the coordinates of basis B are converted to the coordinates of basis C. So a little love note here, that multiplication by the change of coordinates matrix from basis B to basis C converts the B coordinates to basis C coordinates. So if we think about the change of basis in Rn, in the vector space Rn, we realize that we've already been working with this. So let's take a look. If we let basis B be the basis defined by vectors b sub 1 through b sub n, and we let E be the standard basis defined by the elementary vectors in Rn, then we realize that the coordinates of basis B relative to the standard basis are simply the vectors of basis B. So we have the coordinates of basis B. So the coordinates of vector b sub 1 relative to the elementary vectors or relative to that standard basis is equal to vector b sub 1. The coordinates of vector b sub 2 relative to that standard basis is equal to vector b sub 2. And this continues all the way to the coordinates of vector b sub n relative to that standard basis, E. That's simply just vector b sub n. So in this case, the change of coordinates matrix from basis B to basis E, the standard basis, is the same change of coordinates matrix that we were first introduced to. So in other words, the change of coordinates matrix from basis B to that standard basis, which we now know is defined as the matrix whose column vectors are the coordinate vectors of basis B relative to the standard basis. So this change of coordinates matrix from basis B to the standard basis is in fact equivalent to the original change of coordinates matrix relative to basis B, which is a matrix whose column vectors are simply defined by the vectors of the basis. So if you're still having trouble making that connection to see that we've already been working with change of basis, I want you to recall the definition for the coordinates of vector x relative to basis B. And so if B defined by the set of vectors b sub 1 through b sub n, if this is a basis, then we know the following. Then the coordinates of vector x relative to the basis B are the weights or scalars or coefficients that satisfy the vector equation. So we have that vector equation, vector x is equal to scalar c sub 1 times vector b sub 1 plus all the way to plus c sub n times vector b sub n. And this, of course, is such that c sub 1 through c sub n are those weights, those scalars, those coefficients. So we have this vector equation, and we can recall that we can convert this vector equation to the equivalent matrix equation. So we have a matrix whose column vectors are defined by the vectors in the basis, multiplied by a column vector whose components are defined by the weights. And so we can rewrite this as the change of coordinates matrix relative to the basis B multiplied by the coordinates of vector x relative to basis B. And so what we just observed with the change of basis in Rn is that saying that vector x is equal to the change of coordinates matrix relative to basis B multiplied by the coordinates of vector x relative to basis B is analogous to saying that the coordinates of vector x relative to the standard basis is equal to the change of coordinates matrix from basis B to the standard basis multiplied by the coordinates of vector x relative to basis B. So these are in fact equivalent. And if we still need a little help in seeing this, we can again simply think about the definition for the coordinates of vector x relative to the standard basis. So since E is the set of vectors, e sub 1 all the way to e sub n, the elementary vectors, is the standard basis, then the coordinates of vector x relative to the standard basis are the weights or scalars or coefficients that satisfy the following vector equation. That satisfy the vector equation x being equal to x sub 1 times the elementary vector e sub 1 all the way to x sub n multiplied by the elementary vector e sub n. And this again is such that x sub 1 all the way to x sub n are the weights. And again, we know that we can convert this vector equation to a matrix equation. So we have the matrix whose column vectors are defined by the elementary vectors multiplied by a column vector of weights. Now, of course, we could say that this matrix here, whose column vectors are the elementary vectors, is the change of coordinates matrix relative to basis E, but we actually know this better simply as the identity matrix. So this is the identity matrix in Rn multiplied by the vector, or by the coordinates of vector x relative to basis E, that standard basis, which by definition, or by properties of matrix and vector multiplication, this simply leaves us with the coordinates of vector x relative to the standard basis, which is equal to vector x. Woohoo! So again, we have been working with change of basis. But from this point forward, we're going to look at slightly more exciting cases than mapping a basis B to the standard basis. But the process the computation behind it is still the same.